Hello and welcome to this EE328 lecture video on the fast Fourier transform. So the fast Fourier transform is a specific algorithmic implementation used to compute the discrete Fourier transform. So the DFT is, by definition, evaluated for n different samples, and it looks like the sum of the time domain signal times the root of unity that you see here, and that is done for over n times. So if we're going to compare the algorithmic implementation of the DFT to computing the DFT by definition, then we should first establish how many operations it would take to do the DFT by definition. And so if we look at this sum carefully, there are n terms, which means there are technically n minus 1 additions. And then that is done n times. And then also within each of these sums, there are n multiplications, because every term has a multiplication between these two factors. And so together, there are n plus n minus 1 operations per sum, and that there are n sums to be done, and so we get something that looks like n times 2n minus 1 operations. Now, when we're comparing algorithmic complexities, what is typically done is we throw away scaling factors out in front of these functions, and we also tend to throw away lower order components of the functions. And so what you'll see is that this technically is 2 times n squared minus n operations per DFT. What you'll see is in algorithmic complexity literature, this is referred to as big O of n squared. And the idea being is that we don't, when n is getting large, we don't care about a constant factor out in front, and we also don't care about a lower order subtraction or addition out here. Is that when n gets large, the only term that will dominate is n squared. In order to develop the FFT, we are going to need a couple of fundamental results. And the first is that just taking the DFT of a single number, so your sample has length n equals 1, is just the number itself. So the DFT of a signal of length 1 is just the signal itself. So this is the convention I'm going to use in these slides, is that capital letters refer to DFT quantities and lowercase letters refer to time domain quantities. So the next fundamental result is that if you have a length 2 sequence, so n equals 2, the DFT will also be length 2, and if you clip your summations to be from 0 to 1 now, then we are looking at, this is x of 0 times e to the 0 plus x of 1 times e to the minus j 2 pi times 0 times 1 divided by n. So just a heads up that this k equals 0 is where this 0 comes from, and this n equals 1 is where this 1 comes from. So either way, both of these are 1, positive 1, and so the 0th element of the DFT of a length 2 sequence is simply the sum of the samples. Now if you increment k, so now k equals 1, now all of a sudden here n equals 0, and so we're still going to get e to the 0. Here n equals 1 and k equals 1, so we're going to get a multiplying factor of e to the minus j times 2 pi times 1 divided by n. In this case n equals 2, and so we get e to the minus j pi, which is the same as negative 1. So that's where this negative sign comes from. So the second value of the DFT of a length 2 sequence is simply the difference between the first and the second time samples. It's not like these particular DFTs give us really any useful signal information or frequency information about a signal, but we're going to use them because we're going to break down a big problem into lots of simple problems, and in the limit, those simple problems will come down to these kind of operations. So the biggest insight in computing the FFT or developing the fast Fourier transform is this notion of divide and conquer. And so the line that we're going to divide down is even and odd. Let me walk you through the development of that first. So for starters, I'm going to make a pretty mild assumption. I'm going to assume that n is even. And in fact, at the very end, we're going to assume n is a power of 2, which means it has to be even. But this is not like you can take the DFT of odd length signals, but if we make this assumption, it cleans up a lot of the math in this derivation. Everything that I'm going to say holds for odd length samples, but the arithmetic is filled with like floor and ceiling operators that kind of muddy the water unnecessarily. Okay, so for what follows, if I write n over 2, that's going to be an integer. So no one has to worry about splitting halves. And then the other thing is I want to kind of abbreviate this number, which for a fixed capital N is just a fixed complex number. So I'm going to call that W sub n, and it's simply the nth root of unity here in the complex plane. Okay, so if we use this notation, then all of a sudden we can write the definition of the DFT in terms of W sub n to the n times k, right? Because if I write W sub n raised to a power, that's e to the minus j 2 pi over n raised to that power, which is the exact exponent we want, e to the minus j 2 pi little n times little k divided by big N. And since this summation is an even number in length, we can divide up the sum into the even terms, or the terms that lie on an even index, really, is what I meant. Even indices and odd indices. And then note that the sums are running to half of their previous values. And so because we're skipping over integers now, we also have to skip over integers here and skip over integers here. So it's like subbing in for every little n a 2n and a 2n plus 1 in the second sum. Okay, if you were to recombine these two sums again, you would recover the first summation. I'm just splitting them into two separate summations. And so the benefit of doing this is that this term now looks like W sub n to the 2nk plus k, and the k is not being summed, and so it actually pops out here. And now I have W sub n to the 2nk in both of these sums. And let's take a look at what that can be broken down into. So W sub n raised to the 2nk is just e to the minus j 2 pi over n times 2 times little n times k. But multiplying by 2 is the same as dividing by a half, so I'm going to do a little trick here. And I am going to keep the 2 pi and the little n and the little k up there, but instead of multiplying by 2, I'm going to divide by a half. And so if I write it this way, all of a sudden this is W sub n over 2 raised to the nk. And so that's how we transform this into that, and this into that. So the benefit of doing this is that now I hope you see that this looks like a DFT of a shorter sequence. This looks like a DFT of length n over 2, right? Because if we're just looking at the even indices of x, there are only n over 2 of them, and the unity that we're looking at out here is of length n over 2. And the same thing over here. So this is also a DFT of length n over 2. So this is what I mean by divide and conquer. To get a full length n DFT, you can decompose the problem into two DFTs, each of which are shorter. It seems like we haven't gotten anywhere, but this will actually lead to an efficiency in computation. Each of those two DFTs I'm going to call sub-DFTs, basically. They are DFTs of shorter length signals, and so their DFT length will be shorter. However, there's nothing stopping us from evaluating the sub-DFT at all of these k indices, right? Even though the only k's for which there are new values are n over 2 minus 1, there are more k values that we could plug in, and we're guaranteed repetition, right? So the DFT is always periodic, and it's periodic with period the length of the time signal. And so if I cut the length of the time signal in half, the DFT period is halved, but there's nothing stopping me from evaluating one period and then the next period. And so that's what we're doing here. We're evaluating 2 periods worth of each sub-DFT. This is x sub e of n. That's the signal comprised of the even indexed samples of the original signal. And this is x sub o of n, which is the signal comprised of the odd indexed signals. And so here's where evaluating those sub-DFTs in the second period comes into practice. So again, we are writing the full DFT as the sum of two sub-DFTs with a scaling factor. But the sub-DFTs are going to be shorter DFTs. So in particular, if I'm just evaluating them at within their first period, then there's no funny business. Then I can just evaluate exactly what I have written up here, down there. But when I go and wrap around into the second period, I'm going to use the same index, k, and to indicate that I'm going into the second period, I'm then going to add n over 2 samples to the index. Okay, so I am simply plugging in k plus big N over 2 into this equation, and that's what I get here. But here's where we capitalize on the periodicity. It's because xe is n over 2 periodic, and because xo is also n over 2 periodic, I don't have to look k plus n over 2, I can simply look at k. And the last trick is we are simplifying this multiplication factor down to this multiplication factor because, again, a property of the exponential. If I take w sub n and I raise it to the k plus big N over 2, then that's e to the minus j 2 pi over big N times quantity k plus n over 2. That is the same as e to the minus j 2 pi k over n times e to the minus j pi, because the n's will cancel and the 2's will cancel, and this is negative 1. So that's where that negative sign comes from. And then we can simplify this to be the same multiplying factor in both of these expressions. We are going to capitalize on this symmetry because to calculate the full DFT, we only need to do 2 sub-DFTs. And we can represent that graphically in what's called a butterfly diagram. So let's say that we have big X sub e. So someone hands us that, and we also are given big X sub o. So if we take big X sub o and we multiply it by this multiplicative factor, w sub n. So remember, these are vectors. You can think of them as column vectors because they are valid for a bunch of these different k's. And w of n is going to be the column vector of wn0, wn1, all the way up to wn n over 2 minus 1. Okay, so then we're doing element-wise multiplication in this multiply block, and then we're going to do a subtraction here and an addition here. So here is where the butterfly diagram gets its name, is because the wings of the butterfly cross over here. So this is a pickoff, this is a pickoff. These two don't touch, and then we are doing a plus and a minus sign there, and a plus sign there. And so algebraically, what do we get? We get x sub e plus w sub n x sub o, and we get down here x sub e minus w sub n x sub o. And if you like, we can glue these two together and get the full DFT. Okay, so again, this is length n over 2. This is length n over 2. And this one is length n, because we're gluing two things that are length n over 2 together. Let's compare operations here, shall we? There are, let's do it in a different color. Here, there are n over 2 multiplies, because these vectors are both n over 2 long. Here, there are n over 2 subtractions, and here there are n over 2 additions. So if your butterfly produces a vector of length n, that butterfly requires 3n over 2 operations for result of length n. So let's see how we can capitalize on this divide and conquer structure to simplify or to minimize the number of operations that we need to do. So this is the number of operations for a single butterfly, but the real cool thing about the FFT is that you actually reduce the number of butterflies that you might otherwise need. So let's draw this in the same direction. So I'm going to start with a big old vector, and this is where we're going to end up. So this is the full DFT, and it is of length n. So I'll draw that down here. Okay, and so what we just said is that we can build this out of the gluing together of two subsequences. So I'm going to copy that butterfly. Here's a multiply, here's an add, and then we pick off and add there, we pick off and add there. And I think I'm going to neglect the subtract sign because it's actually not terribly relevant, because we're going to count additions and subtractions as the same number of operations. And so this, we need something half as long. And this was multiplied by w sub n. And this was the x sub o, if you remember from the last slide, and x sub e. Okay, so this is just copying the butterfly from the last slide and making it much taller. And we're going to do that because there is a recursion to be found here. Because when we have shrunk our length by a factor of 2, what we're left with are simply two DFT problems, right? This array capital X sub e is simply a DFT, which means that we can copy this butterfly, and that means that XE is actually a glue together of two sub-DFTs. So multiply, add, and then this is going to be half as tall as the last. And this is going to be half as tall as the last. And then same thing down here. This is half as tall as the last. This is half as tall as the last. And this now, the signal that we're, or the vector that we're multiplying here, these are both w sub n over 2, w sub n over 2. And yeah, so we haven't actually given these sub-DFTs names, but I think it makes sense to call this one XEE, so the even part of the even part, XEO, the odd part of the even part, XOE, the even part of the odd part, and XOO, the odd part of the odd part. Okay, so we have now dropped our length to n over 4, and by now I think you see the pattern, so I'm actually going to kind of dot this until we get to 2 length 1 DFTs, which aren't actually DFTs, right? They're just the signal themselves. And then the same little mini butterfly structure. And so this is repeated down here until in this stage our length is 1, and in this stage our length is 2. And there's a dot between there. Let's tally up the number of operations in each stage. So let's go to orange. And so we established on the previous slide that if the result of your butterfly is length n, then there are 3n over 2 operations. So it stands to reason that if your result of your butterfly is of length n over 2, then there are going to be half as many operations. So this butterfly gives us 3n over 4 operations. This butterfly gives us 3n over 4 operations. But since there are 2 butterflies, then together there are still 3n over 2 operations. Okay, so that's because you are multiplying by 2 the number of butterflies you get, working your way backwards in this diagram, but also each butterfly has half as many operations. So the total number of operations per, if you like, butterfly stage is constant, and it's a constant times n. So we say that it's linear in n. So then the complexity of this algorithm will then depend on the number of butterfly stages. So let's work that out. So to go from 1 to n requires log 2 over n plus 1 stages. So there would be log 2 of n plus 1 red numbers here. Right, so let's take, for example, if big N were 4, then I would have 1, 2, 4. Log 2 of 4 is 2, so I'd have 3 numbers. But we're not counting the stages, we're counting the hops between the stages. So we get log 2n plus 1 minus 1, because there's 1 fewer hop than there is stages. Or butterfly sets, if you like. And each butterfly set requires 3n over 2 operations, and so what we get is a complexity that looks like n log n. Okay, so again, I'm kind of discounting the constant factor times the n, so we don't have to write the 3 over 2. But we have this many butterfly stages and roughly this many operations per butterfly stage. And so what you get is a reduction in complexity or runtime, whatever you like, by implementing this divide and conquer FFT methodology as opposed to doing it by definition. I should mention that we have, I've kind of silently made this assumption in this slide, and that is that this decrementing by a power of 2 every time gets you an even number of results. And I think you've heard Professor Pilkington mention that if your n is not a power of 2, often you will have you will see a runtime improvement if you just pad with zeros until you get to the next power of 2. So to convince you one last time that this is actually an improvement, and a significant one than something that runs in n squared time. I have a quick MATLAB graph of the two functions here, n log n and n squared. Okay, so on screen here is just the values of n squared in blue versus n log n in orange. And so on the horizontal we have the number of samples in the DFT, and I'm only picking powers of 2 because that's the only fair comparison really here. And so all I'm going to do is I'm going to start, and you can see that for even DFTs of length, this is a log scale, so this is going to be length 16 over here and length 8 over here. Even for relatively short FFT operations, the FFT actually beats out the definition. But we can see that the factor by which it beats it out grows actually really quickly. So let's try another xlim. And so if we zoom out on the x-axis progressively further and further, we can see that the n squared runtime starts to become unimaginably bigger than the n log n runtime. And so the performance enhancements you get from running FFT versus the DFT by definition are quite significant, especially when the sizes of your DFTs become quite large. Okay, I hope you enjoyed this video, and I will see you in class.